Tidal wetland stability in the face of human impacts and sea level rise. This was a secondary source done by Kirwan and Megonigal. As an introduction, it's important to understand that coastal wetlands have great value economically, but are at risk. In fact, 25 to 50% of coastal tidal wetlands in the world have been converted into agriculture land or used for aquaculture. It's predicted that we will have a 20 to 45% loss of salt marsh due to sea level rise in this century. Yet, to give us some hope, there's limited historical record of salt marsh loss due to sea level rise. In this article, they'll be talking about feedbacks between flooding, plant growth, and elevation that will stabilize submerging wetlands. Some coastal tidal wetlands include salt marshes, mangrove swamps, and tidal freshwater marshes. The purposes for this article were to discuss what influences how coastal tidal wetlands adapt to sea level rise, and to explain how changing socioeconomic condition and climate may change our current understanding of this feedback in ecology and geomorphology. This article argues that, quote, interactions between sea level rise and human impacts will drive wetland stability in the future. So the first thing we're going to talk about are the biophysical feedbacks that stabilize wetlands. Tidal wetlands span across 20 million hectares and over the last 4,000 years have experienced sea level rise of approximately 2 meters. Drowning of wetlands is very infrequent because of their ability to engineer their position in the intertidal zone. One way they do this is through vertical changes in elevation. This occurs both above ground and below ground. Above ground, the wetlands can experience tidal flooding, in which the minerals settle out of the water column and into the soil. Thus, the deposition is highest in areas that are flooded more frequently and lowest in areas that are less frequently inundated with water. Below ground, plant root growth and decay in the soil profile raises the elevation of the water. Next, we'll talk about the threshold rates of sea level rise. The first one is wetland deterioration. These are areas of marsh that are converted to open water, and this occurs in areas with low elevation and high rates of sea level rise. This does not stimulate plant growth in these tidal wetlands and leads to a transition from a stable to unstable condition. Another factor that affects whether a wetland is stable or unstable is the availability of sediment for accretion. When comparing historical data to now, we see that sea level rise was approximately 1 millimeter per year for the last 2,000 years, but has sped up to today's rate of 2 to 3 millimeters per year around the late 1800s. In this table, the top image shows a marsh and the bottom image shows a mangrove, both of which use their own set of horizontal and vertical scales to influence their stability. The image on the right shows how elevation can change above and below ground, and then uses different colored arrows to show different factors that it can influence these things. The green arrows show local factors. The blue arrows show large-scale climatic and geomorphic processes, and the orange arrows show political, social, and economic factors, which can affect all the other processes. Now we'll talk about human interference with ecosystem feedbacks. Historical cues as to what amount of sea level rise tidal wetlands can handle are limited by differences between the past, present, and future conditions of the environment. The present environment has higher atmospheric carbon dioxide concentration and has more plant-available nitrogen, as well as higher temperature and higher plant and animal species that will affect how well they can stabilize. Climate change and eutrophication depend on above versus below ground effects. We also have limited ability to forecast how tidal wetlands will respond because of a limited experimental design. When considering eutrophication, you might think this would be a great way to enhance elevation of these marshes and coastal areas, but in an experiment done at a Caribbean mangrove swamp, nitrogen was added and there was a decrease in elevation at the fringe and interior portions of the swamp, even though the areas in between those two sites were not affected. And then when phosphorus was added to the swamp, elevation decreased at the fringe but increased everywhere else. So these differences in responses were driven by below-ground processes and differences in affine root growth, which were affected by the initial levels of nitrogen and phosphorus in the system. To continue talking about human interference with ecosystem feedbacks, we'll talk about vegetation shifts. New species can have large impacts on this ecosystem by adding or subtracting traits that can impact the ecogeomorphic feedbacks. Sediment levels also greatly impact coastal wetlands' ability to survive. The subsidence or sinking of wetlands aligns with the estimates of hydrocarbon extraction, and the patterns of wetlands lost in Louisiana align with the density of oil and gas canals built in the state. Dams and reservoirs prevent about 20% of the world's sediment load from getting into the coast. Throughout the world, regions like the Gulf of Mexico, Venice Lagoon, and Chesapeake Bay are each regions experiencing wetland to open water conversions and are also sediment deficient. Here's another table from the article, and from the bottom we can see even if sea level rise remains stable, things like dam construction and reforestation can lower sediment yield to the coast and will lead to stable wetlands becoming more prone to collapse. So what are some of the direct things humans have done to modify wetlands? In the 20th century, 20 to 50% of the world's coastal wetlands were reclaimed for other uses. Intentional conversion of tidal marshes in developed countries has slowed due to education and thus conservation efforts and laws. Developing countries are still converting their tidal marshes for agriculture, aquaculture, and tourism purposes. As far as socioeconomic factors go, economic factors have actually incentivized creating more arable land, even at the cost of tidal wetlands. According to the article, the fate of our wetlands, quote, depends on socioeconomic conditions, policy decisions, and perceptions about the value of coastal wetlands. In this figure from the article, we see 4 examples of wetland conversion. In the first one, mangroves were cut and filled with substrate to create white beaches and belize. In the second image, we see an aerial view of mangrove swamps that were converted into fish ponds. In the next image, we see a seawall that's preventing a tidal marsh from migrating landward. And in the last one, it's an image from California, and we see the collapse of a tidal freshwater peat after being drained and farmed. In the future, not only will we need to use technologies to analyze wetlands further, but we'll also need to understand human perceptions of the value of wetlands. From this article, the author gives us 2 main insights. One is that biophysical feedbacks allow wetlands to survive, which will allow for longevity and potential restoration. And the second is that historical adaptations to sea level rise indicate that the loss of wetlands may not be the outcome of this climate change. Rather, the wetlands will adapt for their survival. One way they could do this would be by moving landward. As a closing statement, the authors propose that the rates of climate change may not be what impact wetlands as much as the sociological and economic decisions that we make to protect our coastal infrastructure. Here are my citations. And finally, let's go over some discussion questions. My first one is, how could we go about stopping wetland conversion in developing countries for agriculture and aquaculture purposes? And also, how might this research inform management and policy decisions?